Thank you for showing up. Today I'm going to talk about our paper, weight sharing regularization. I have led this paper with Marwan, with the supervision of Simon and Siomek. This paper was recently accepted at AI Stat. This is my first time presenting it. I'm excited to share it with you. Feel free to jump in if you needed any clarification. And I invite also Mehran and Simon to jump in if they needed to add any extra insights. Okay, the starting point of our paper is to emphasize on the importance of weight sharing in neural network. Almost all of the popular architecture for neural network use some form of weight sharing. CNN is the most famous example where there is this convolution filters that are shared and are taken over the pixels of image. This is the shared weight. Transformers also use some form of weight sharing too. So weight sharing is important in the context of deep learning. This is from the practical point of view, but also theoretically, there are results that prove that requiring a linear map to be symmetric with respect to the permutation group induces weight sharing in the matrix form of the network. So it was proven theoretically and practically the weight sharing is important to have in a neural network. However, the weight sharings are mostly hard-coded in the network. So there is this assumption on how the weight sharing should be, and it is hard-coded in some specific way in the networks. In this paper, we aim to learn these weight sharing patterns instead of just accepting some form of it and accepting as a bias for the network. And we're going to add it as a regularization. Again, on the importance of regularization, we all know that it reduces overfitting and improves generalization. These are two most common and important regularization in neural networks. L2 encourages weights to have less L2 norm, and L1 norm encourages sparsity in neural network. As you see, W1 is selected to be 0 in this L1 in this picture. So we are adding weight sharing regularization. Here is how it looks like. So we are encouraging the WIs and WJs to be close, each single weights in the network. We are encouraging them to be close to each other. This is what we are adding to the loss, along with an L1 term. So we're encouraging the weights to be close. So we are minimizing the loss along with encouraging weights to be close, encouraging weights to be sparse. The sparsity part, yes. Yes, I try to use this. Yeah.
Global mic. This should be. I just activated this mic, so this.
Hello.
This is working, and normally you don't have to. Okay.
So can you hear us fine online? So you say we can hear. Okay, perfect. Okay.
Amazing. So we are adding this extra regularization term to the loss along with L1. The R is going to encourage weights to be the same as each other as much as possible. The point of L1 is to kind of make the clusters of weights that are shared to be 0. Imagine that we are adding the R term, and some shared weights are induced. And then in the deep learning setting, it's ideal that those shared weights are 0 if there is a lot of shared weights appearing in the network. Also, we know that L2 is a ball and L1 is a ball too, so it's a norm. So it has a unit ball. And R plus L1 is a unit ball too. R alone is not a norm, so it does not have a unit ball. And it's interesting to see that R is actually a pseudonorm. It's not a norm, it's a pseudonorm. And the only property that it does not satisfy is the zero property. So norms should have this property that if a norm is zero if and only if its input is zero. So it's saying if R is zero, WI should be zero too. However, we don't have it in R. That's the same motivation as I gave practically. By adding L1, we are satisfying this extra property that we want to. So the property is that if this term is zero, the W is zero too. So this is another motivation for adding L1.
It's just given that you're talking at the screen, I wanted to move the camera so that we can see you in the screen.
Oh, I thought the camera was to detect.
Oh. You don't have a remote, it's just this? Yeah, I can do it here.
So, just to be sure, Motahareh, so you put this weight chain regularization on all the weights?
On all the ways,
Like not
but
layer by
in a layer wise.
Oh, layer wise, okay,
yeah.
okay, so.
But we don't, like throughout our paper, we don't make this restriction that it should be layer wise for in the whole network, but in our experiments, we do that layer wise.
So like, to constrain the weight inside your layer.
Yes, in a layer, there should be close to each other. Yeah.
And even if the layer is not fully connected, like for instance in convolution you have like just a local effect if you check one weight. In that case, it doesn't make more sense to have the W1 and WD to be close to each other. Mm-hmm. So I don't know if you adapt this also.
So our goal is to add this regularization to a fully connected neural network. So we're not adding to this regularization on top of convolution. Okay. Actually, if we add this regularization to a fully connected neural network, we can see that the sparseness and the weight sharing appears just like the Sienna.
Okay, okay.
Okay, so this is the regularization that we are adding. In the literature, it's known as clustered lasso. But it was not a really successful regularizer in the literature. First, it was used only on the linear regression. And secondly, as you can see here, they are not really successful in solving it. They are saying, I'll read it out loud. They are saying that for p less than 110, we solve this with the convex optimizers with p less than 110. This seriously restricts the use of clustered lasso in the real world applications. So the dimension that they could give algorithms for this regularization in linear regression in a very easier setup than ours was 110 dimension. A spoiler is that we're gonna apply this to a neural network by the end of the talk. So we're gonna expand this. This is one of the main contributions of the work. But starting with this regularization term, there will be some problems. The first one is that it is non-differentiable. This L1 norm, this absolute value makes the term non-differentiable. The first solution that optimizers think of is to use to solve it with the subgradient method. Subgradient method is like the gradient descent, but it uses subgradients, which is kind of a generalization of gradients for non-differentiable case. We quickly see the definitions here. It's going to be useful for the rest of the talk too. Can we get rid of this?
Is it on you or is it for?
Maybe for me actually. So subgradients definition is this. Let me just quickly draw the famous and easy example of subgradient, which is the absolute value. The absolute value has gradients in this region. In this region, it is -1 is in this region, 1 in this region. But here is the point of non-differentiability. What people do is to draw convex lower bounds and accept all of these lines as subgradients. So we don't have one gradient anymore. We have a set of subdifferential, which refers to all of the subgradients at this point. So at this point, specifically, all of the set -1 to 1 is accepted as the subgradient if you want to do the gradient. The subgradient method, however, is not really desirable to use because of a bunch of problems. There has been some work that's shown that because imagine you want the networks to be sparse, exactly at the optimal point of the L1, you get the non-differentiability, and this makes the optimization process very hard. In this paper, they showed that this makes the network not be able to make the weights small enough not to detect the sparsity pattern properly. This is this result. L1 with gradient descent is the orange line, and the optimal sparsity pattern, which was computed separately, is the gray dashed lines. So you see that L1 with subgradient cannot successfully retrieve the sparsity pattern. Also, there's the second point that the convergence rate of subgradients is slow with respect to another method, which we're going to use, which is proximal gradient descent. So we're not going to use subgradient method. Instead, we'll use proximal gradient descent. I will quickly give an intuition of how proximal gradient descent work. There are some derivations, but I'm not going to go over the derivation. I'm just going to convince you that this is a good method, a reasonable method to work with. The proximal gradient descent is mostly suitable when you have a composite function. One of them is differentiable. It's like the loss functions of neural networks, everything is good. And the other one, the second half, the edge function, is non-differentiable. So it's suited for this setup. It proposes to do a simple gradient step in the differentiable function. However, and take this point, x hat, that you did a simple gradient descent step, take it, stay close to it, so remain in this ball around the x hat that you just obtained, and then minimize h of u around this ball. This is the intuition of proximal point method. The hope is that we can solve this argument exactly. Actually, for most of important functions, important h's in the literature of machine learning, we can solve this argument exactly. And if we can solve this argument exactly, the next iteration is obtained with the solution. So yeah, this is the proximal, and what we're going to do is to obtain this argument for our new regularization term that we added. Yes.
Is there a coefficient missing in the argument of the argument, like the eta should solve somewhere, or how do I control the importance of the closeness term?
Here, I see what you mean. There is a t here in the derivation of proximal method, but it's usually considered to be 1.
Okay.
Like if you write it and if you write it, you will see a t appears here. That's correct.
But this is the method that you're considering.
Yes.
It's not a type of discussion.
It's not a type, yeah. So yeah, this is a more precise way of writing it. We call this a proximal operator. So whenever I call the proximal, this is the argument that we are solving. If h is convex, this quadratic term makes it strongly convex. So this argument exists and the solution is unique. So everything is cool, and we can find the prox, hopefully, and do this, the minimization of G easily. The optimality condition is kind of the same, but for the non-differentiable function. 0 should be in the subgradient of this, and the gradient, which is u minus x. This is the optimality condition.
I think your eta was mixing. If you look at the equation at 8, you will have the prox with not h, but eta.
Mm-hmm. But that eta is referring to...
Because you use the same eta, so that they cancel out.
Hot eta h, you return like whatever to eta. If you
Correct.
take h as a scalar,
Yeah, exactly.
so I think there is no typo with this.
No, but the prox is fine. The prox, that's the definition, is in the previous method. If you go back one time,
Okay, there's no typo, it's just, it's
Here,
used
there,
for the
there should have been two eta.
Oh, yeah.
Actually, yeah. This one. The third line, the third equation,
What about-
we're missing a one.
Oh,
two
One
eta.
over two, it's, okay.
So equation A is correct. Definition of proximal mapping is correct. It's just.
Yeah, that's right. Great. So let's see quickly the example of this, the norm f of x is equal to absolute value of x. This is the prox. As I said, this is the self-differential. If we just write the optimality condition, we can get the u. So this is going to be our rule. If you give me an x and you want the L1 prox of it, I will subtract one or add one depending on where it lies in the spectrum. So -1, 1. If you give me a point here, I will subtract 1. If you give me a point here, I will add 1 to it. And if any point lies in here, it's gonna fall into 0. So it's shrinking every point and then making the points that lie in that are small enough 0. However, ours computation is not this easy. We're going to get to it. So the next slide is going to be dedicated to computing the proximal of R, the regularization term that we introduced. Let's first compute the subdifferential of R. This is the form of R. We know that R is convex and it is piecewise linear. If you want to work on it, keeping the absolute values there it's hard to see what is the value of function because we want to see the pieces, how they look like to get the gradient. So we should assume some sort of ordering. We assume that we have access to the sorted version of the W. If we have access, if we can sort the W's, we can measure the absolute value easily. So for the Wi, there are I-1 points that the result of that subtraction is Wi is greater than them. So the result of the subtraction is positive. And there are D-I points where the result of that subtraction is negative. So Wi is going to appear with the negative sign. So it's going to be Wj minus Wi. So the hyperplane that will resolve is this. So these are with negative signs, so it's going to be I minus d plus I minus 1. It's going to be 2I minus d minus 1. This is going to be the coefficient of W. These are all of these hyperplanes. And we might have, so this is R. If we just have, this is R, exactly. If we have access to a sorting, we can compute R, exactly. So what is the subdifferential of R now? If you have multiple sorting that are valid, this happens when you have some of the, so if Wi is equal to Wj equals to Wk, you can just flip the orders and this is still sorted. So we have multiple sorting. So the subdifferential of R is convex hull of all of these sorted ties. It is not a proof, what I just described. We have the extensive proof in the paper, but this is kind of an intuitive understanding. It kind of matches with our understanding of the absolute value function too. So here in the point of non-differentiability, you're kind of taking the convex hull of this -1 and 1. So this is the subdifferential. The same thing happens here. You're taking, because the non-differentiability in the R happens when the weights are equal, when you have multiple sorting. The weights are equal, you have multiple sorting, so you have to take the convex hull of all of these gradients. Yep. Here comes the.
So here, if I don't want to have all the pi here, is it the case that R of W is the soup over all pi of H pi of W?
The supremum happens when the weights are sorted.
Good. So I could, because here pi depends on W, which is kind of. So if I don't want to worry about which pi corresponds to which W, I can just write it as, like here it's the max of the two
Exactly.
things. So I could also do
Yeah.
max overall pi of these H pi W, right? Every pi I have a plane.
Yeah, that's right. But in that view, so this is kind of good to deepen the understanding. So how many hyperplanes does the R have? Possibly. Can anyone help? It's n factorial. You didn't count, but yeah.
Yeah, but in the case where everything has the same value. And is the number of the block.
So it's d factorial. The dimension of W is d, so there are d factorial pieces.
Yeah, but that happens when all W have the same value.
Yes.
That's just our worst case. In most cases, it won't be
Yeah, exactly. But only the ones that are sorted are the ones that. So it's like here. So you have this hyperplane, and the supremum, the pointwise maximum, is the valid hyperplane. Yeah, the supremum point of view was kind of, I found it a bit confusing because I am talking about n factorial hyperplanes, but that's a good.
But also you just need one. So even if the number of valid hyperplane are is exponential, we just need one valid.
Yes,
Okay.
we just need the sorted ones.
Yeah.
That's right. So here we got the subdifferential. We found out how to evaluate R. We found out how to get the subdifferential of R. But we want to get the prox. That's our goal. We should not forget that goal. The way that we compute the prox is sort of non-conventional way of doing it, but it's cute and kind of creative. So we write an ODE and then compute prox based on ODE. Let's see what is this ODE saying. It's saying that W dot, the velocity of each W is this. What is this? It's just one member in the subdifferential. So subdifferential is the convex hull of all of these subgradients. One member, and basically a trivial member of this convex hull, could be the mean of the knowledge. So the mean of all of the sorted H. That's what we are setting the ODE velocity to be. So we kind of get one member of this subdifferential and we set the W dot to be that. So the velocity of weights are this. This is the ODE that is gonna rule over our work. Yes.
In the one-dimensional analogy with the absolute value, that mean is zero, right? Am I reading it correctly?
That mean would be zero? No. I mean, it depends where are you computing it. If you're computing it here, that mean is gonna be -1. And if you're
Yeah, at that point there's only one subgradient, so there's no confusion.
So there's one
zero
sorted
is the
hyperplane.
case.
Yeah, in the zero case.
And then you were talking like, okay, this
Yes,
is like,
it is.
it's like +1 -1, so.
Yeah, it is zero. It is zero. Actually, this is one of the properties of the system that I'll talk about later. The momentum is conserved in the network. That's what. But yeah. So this is the ODE that we introduced. It has some nice properties. First, it preserves weight sharing. So if you have Wi and Wj that are equal, they will remain equal. Their velocities is going to be the same. So they will move along with each other. They kind of stick to each other. And as a result of this, we have the monotonic inclusion. So if you have a sorted W and you move some step further, it means that some weights are getting equal and they are sticking to each other. So in the next step, they are still included in the next sorting, because and in each step you are only adding to the equal weights. So the rest of the weights is going to be the same. So the sorted systems in time 1 is a subset of sorted system in time T2. And the subdifferential is included in the subdifferential of the next time steps as well. This is directly resulting from the definition.
So just to show that, as long as there is no flip, the ordering, so the scale can use it.
There's no flip in ordering. When when two part, like when there is a flip, they stick to each other because their weights is set to do that.
So you cannot flip, the only thing that can happen is that two weights that were different merge to be the one.
Exactly.
There is no flip.
So that's why it's, you have to
You won't pass each other.
You won't
Stick
pass.
together. Another thing also important to recall here is that grain of H doesn't depend on W. So if you go back to the subdifferential, I guess.
It's just linear, so this gradient is just constant.
Correct.
Yeah.
So at the bottom equation 11, you have the subdifferentiable of R at W is the convex hull of Bloch. It only depends on pi sort. It doesn't depend on W. So the only depends on W is from just the collision. So that's why if the collisions are maintained, then the subdifferential is included. If you just add more collisions, then you have more elements in this union, and so then it gets bigger.
I'll give more intuition about the collisions. But yeah, that's right. So from the inclusion of sorting, immediately the inclusion of subdifferential comes. So because of this. Okay, here's the important theorem of our paper, is that in that ODE, if you follow it for one step, it's gonna give us the price of R exactly. So for one second. Yeah, so if you initialize the W's with the W zeros, W1s, and you move your system, the ODE system, one step ahead. What does this mean? We're gonna talk about it. But if you move the ODE one step ahead, it's gonna give you the prox exactly. So now I'm gonna talk about how is this moving from step 0 to step 1 happens, and what should we do to satisfy it? We're not actually solving the ODE exactly numerically. We're gonna see what does it mean that the ODE moves one step ahead. For that, we have to interpret W and W dots as the states of some physical systems of particles.
Can you provide a bit of intuition why this theorem is true?
Yes, it actually comes from the monotonic inclusion part. So we're moving from step 0 to step 1. At T1 we have gradient 1, G1. At T2 we have G2, which is included it's included in the G1, and the same happens up to the T1, Tn, which is the second one. All of them are included. So Gn is kind of the convex hull of all of the subgradients. That's why it's going to give us the prox. If this is going to exactly satisfy the optimality condition that we wrote.
Can you perhaps show it again?
I can write it again. Yeah, 0 should be in the of F. Actually, R. Oh, this is F. F plus U minus X. Yeah, I should write these exactly to be able to make the connections. But if this inclusions happen, U minus X movement, this will result in the U minus X. This is the change. Actually, these gradients are indicating the change in the from X to U. So it's X minus U. The optimality condition is that this X minus U is a member of the subgradient, which is the case here.
The whole displacement is T1 G1 plus T2 G2 plus up to Tn Gn.
Yes.
That's a convex combination of the G1 up to Gns. And these G1 up to Gns, they are all in the subdifferential at U because of the momentum. One thing to note is that in the ODE, you're always following a subgradient. Because you're averaging some subgradients, and it's a subgradient.
So now we're gonna see how we're gonna deal with the prox operator, because we don't want to compute the ODE numerically.
So maybe one question is standard to compute prox using ODE. I've done a lot of prox and never.
No one does it.
Okay.
Just
No, okay, there are people working on trying to find the reference, but it's known result that in non-smooth optimization, if you try to solve the differential equation instead, it converges in 1 second. Just trying to find the reference, but find it. But it's hard to have intuition because it's fine. I mean, it's not something which I guess changed a lot.
No, but it's good because we have camera ready in 2 days, so if you have the citation, we can add it.
Right. But it's a surprising result because when you try to analyze an algorithm from the continuous time perspective, then in non-smooth optimization, it is notoriously known to be slow in optimization. They converge in just 1 second. Meanwhile, for things in smooth and strongly convex optimization, they converge in exponential time. So it goes really to go to infinity to reach convergence. So it's like a big mismatch between continuous time interpretation, where non-smooth solution seems to be faster, and actually the real world with discrete variable, where smooth and strongly convex optimization converges exponentially fast, compared to one other epsilon square. Yeah. I think the last. Like the sharpness was an acceleration.
I just wanted to clarify, so this is one of your contributions?
Uh-huh.
The theorem.
Yes, so we introduced the ODE, that was our contribution, and then we had to prove that actually how we get the prox from the ODE. This is how we get it.
So basically the regularizer itself had already a name in clustering, cluster lasso literature, but it didn't have this kind of interpretation of the prox operator or the same kind of efficient algorithm that she put.
Yeah, so the intuition that this ODE gives us is enabling us to introduce a new algorithm that is very efficient and parallel time. So yeah, let's see what is this ODE representing as a physical system of particles. We look at each W as the particle, as you saw in the discussions. It matches with how we see the W's moving towards each other. Each weight is known as a sticky particle because they stick to each other, and the system is in 1D space. It preserves momentum. This is and the momentum is 0. So the weights are 1 multiplied by W dot. They're gonna be, some of them are gonna be 0. So the momentum is conserved too in this system. So let's see what is this intuitive physical system that we're gonna replace by ODE. First, if 2 particles collide, they will stick to each other. They will not pass each other. This is from the lemma, weight sharing lemma that we discussed earlier. This is one rule. The second rule that we're gonna enforce is that if we're gonna initialize particles with W's and the velocity of them with minus nabla r. This minus nabla r is exactly our ODE. It's just having the assumption that that this sort set has just one member. So if this is 1, it's going to be minus gradient of h. So we're going to so if we assume that all of the weights are distinct, so our sorting has only one member, the W dots are going to be equal to minus nabla h, which is minus nabla r2. So this is what we initialize the velocity of weights. Did you have a question? Okay. So we initialize the particles with the W's and velocities with nabla r, the gradient of r, and then we move. So we have particles, they have velocities. We move the whole system 1 second ahead. If we move the system 1 second ahead, it's going to give us the prox. The position of this weights, if collided with each other, is going to give us the prox. I hope it's clear. If it's not, I'm going to describe a trivial algorithm that will make it more clear. So some notation remarks. We're going to use x as the positions of particles and v as the velocity of them, and m is the mass of each weight, which is considered to be 1, but when they stick to each other, it increases. And then we define y, which is the movement of particle in the next step. So it's going to be x plus v times 1 second, which is x plus v. We need a sorting for all of our algorithms. We know that the time complexity of parallel sorting is O of d like d, p plus like d. So if you have enough processors, p is the processors, d is the dimension, the vector that you want to sort. Given enough processors, the sorting is log d. But sorting is the first step of all of the algorithm. It's kind of putting a ceiling on the performance of the method. So we're not gonna bring it in the complexity analysis. I'm gonna discuss 3 algorithms. The last one is ours. The first one is imminent collisions. It has this complexity OD and next end collisions d2p plus d like d, and our search collision. So given enough processors, these terms is going to be eliminated. So the depths, let's say, of this algorithm is d like d, and we get an algorithm which is like 3D, which is better than all of the existing.
In the context of neural networks, how much is enough processors?
So these processors, what we mean, for example, a V100 has 5,000 processors. Its number of cores, almost 5,000. So given one V100, we can have weights up to 10 to the power of 10 dimension.
That's did you check that claim empirically?
Yes, we did. Our experiment basically have what is the number? It's about that, and then we write the calculation. So I understand you might be worried that there is a big constant in front of this.
And also, is it like the entire GPU might not be engaged in carrying one calculation?
Yeah, that's right. But yeah, we validated empirically. So let's start with the first algorithm that we can give. We want to solve this systems of particles that have weights. The particles collide if their position passes each other. So given
where do you get this 10 to the 10?
it is mentioned in the paper, but I think if you just do log 2d,
because you still have d divided by p. D is different.
Yeah, for each algorithm is different, but for our algorithm, I think we needed like 2D processors. And then,
we have that if you ignore all the coefficients, just assume everything has like the O D log D like is exactly D log D. Then we say that up to 10 to the 21 with D up to 10 to the 21, you're better on not 10 to the 10.
So you're
Okay.
better with algorithm than the other algorithm, doesn't mean that any of these algorithms are feasible. That's the difference. I'm saying one complexity is better than the other one, up to 10 to the 10. But the other complexity might still be untractable at 10 to the 8 or whatever. That's the part where I was asking.
Yeah.
Which is what his closest question is. Careful with the statement.
Yeah.
So yeah, we're gonna start with the first kind of trivial algorithm that comes to mind when having this. So we have this W, which has W1. This is sorted, so W1, W2 to Wn. So we want to see, we have their positions in the next time step. We want to see what are their final positions. Some of them collide with each other. So we just see which of them collide. So if the Y of this particle is more than this particle, if we take system one step ahead, they collide and they stick to each other. That's basically what the algorithm says. So if the position in time one of the particle is more than another, they stick to each other and a collision happens, a weight sharing happens in this case. So the algorithm is to detect all of these immediate collision. We call them imminent collision. And then you have to just search for each two weights that are besides each other, see where is their position using the weight, which is the kind of the gradient. So you have the position, which is the value of the weight. You have the gradient, which is the velocity. See where does this weight go in the next step, if it has any collision with the next weights nearby it, if they merge with each other or not. If they merge them, and if they didn't, just keep them in the place. Imminent collision is fast when the total number of the collisions is small, but it's slow when there are a lot of collisions and a large cluster of particles form. Yeah, I hope it's clear. We can see a bad example of a worst case example for the imminent collision. For example, if this is 1, so I'm writing the vector of y, and the rest of the weights are just zeros. So this is 1, and it happens like the position is before the next particle, so it should merge with the next particle. So these two merge, and then their velocities is going to be 1/2, 1/2. And then these two merge, the velocities is going to be 1/4, 1/4. So this is going to merge with the next one, with the next one. And this is actually the worst case example, because if we had all of the collisions, if we could see all of the collision in the beginning, we could handle them parallelly. So if imagine you had this collision here too, I could handle this collision and this collision in parallel, but some imminent collisions cause another imminent collision. So they trigger some more collisions. This is the worst case complexity of the algorithm. When each collision is triggering some more collision, it means that there is a large cluster of the particles forming one group.
Why did you use 100 instead of this one?
It's the same. It was just easier to see. Yeah, it's the same. So basically here,
So why go with the more complicated one? The 100.
the reason is that it doesn't, this case, it's not concrete. because I wrote Y. This Y is not created with X and V's. So this is a more realistic
Where you give
example.
X and
Exactly. If you have X and V's, this is gonna emerge, but this is not. It's easier to explain.
Do you keep the same data structure for the weights throughout, like even after the merge? They're kept as a, you know, as a tensor or as a vector with numbers. There's no hashing or anything.
We will make them like we change the tensor to a vector of numbers, and then we do the collisions and we convert them to tensor again.
I see, but so you keep a dense, because essentially you end up having a more and more compressible vector tensor, whichever the structure is, over time because of the matching of numbers. But you're keeping this this flat, uncompressed structure of it.
Mm-hmm. Yes.
Okay.
Yeah, we're not using it because at each gradient step, so this is the proxy step. In the gradient step, the whole weight sharing is ruined, and then we have to share them. We have to compress them again. So it's not trivial that this structure is kept through steps.
Sure.
Yeah.
Well, I mean, one could easily, I mean, maybe not easily, maybe we can talk about this offline, but just think of like reparametrizing the weight,
Mm-hmm.
instead of being a vector that has all the entries as you start with an identity matrix times the dense vector, and then whenever two weights match, you can like switch, let's say the one for, let's say weights 1 and 3 became together, so you move the one from the 3-3 entry to the 1-3 entry. So when you need to get the output, and this is a big sparse matrix that is easy to handle, you need to get the output, you do, so instead of, when you need the value of the vector to carry out a forward, instead of just doing a memory read, you would do a matrix, sparse matrix vector computation. And then the vector over time, you could be zeroing out the remaining entries.
Yeah.
That would be a different data structure that could be more amenable for this
Nice.
kind of.
Yeah. I see what you. Thanks. Suggestion. Yeah, this was the first algorithm that was possible, imminent collision. The second algorithm is end collision, which is a bit more smart. It is saying that if you have these clusters of weights that are going to collide, just start from the first one and see where does this sequence of collisions end. Finish detecting the whole sequence of collisions, and then go to the next one, and then detect that one. It's a more smart algorithm in this sense. This photo is kidding. For us to detect the whole set of particles that are colliding with each other, we need this proposition, which helps us detect the collisions. So it's saying that take the argmin of the average of these yi's. It's going to give you where the mass of the certain of these clusters of weights lie. So if the average of these of the yi's of these weights lie here, it means the center of mass of these weights is going to be here at the end. If you have any weights less than this, so all of these weights are going to be in this cluster. So all of them are going to collide. Find the least argmin and then use it to detect where does the whole cluster end. This is the idea of the end collision, and then using this proposition, we can find collisions more smartly. This is good when there are a large cluster of collisions, and then it's slow when there are very less collision. It's exactly the opposite of the previous algorithm.
So we just switch like you, sometimes you take a vector, you partition it, and you make it run.
So I start from the first weight. I take the argmin
of the average. So I will compute a cumulative sum over until the end of the vector and take the minimum of this cumulative sum divided by their number. And then the minimum of them is going to tell me where is the cluster ending.
Okay, so then you like merge all these.
Yeah, we merge all of them in one cluster. So all of them are equal weights. We're going to merge them. Yeah. I can spend more time giving more intuition on this, but I'm running a bit out of time. So I'm going to move on to our algorithm, the last one.
Because the previous two already.
Yeah, they already existed, but we offered a parallel version of them. So this is the algorithm that we offered, which is more parallelizable. That's why it's going to result in the depths of log 3p. So what are we going to do is we're going to do a divide and conquer based algorithms. We assume that given some number of particles, we assume that we know we already resolved all of the collisions in the right side and in the left side, and we are just going to decide what is happening in the middle. So in the d divided by 2 and d divided 2 by 1, we already merged and handled the right part and the left part. We're just going to merge these two middle collisions. If they don't collide, the problem is solved. If they collide, they might result in more collisions. So we just need to see where is the beginning of and the end of this bigger collision that was induced by this middle collision. So this is I star that we are looking for, and this is J star. So how we're gonna find I star is kind of similar to the previous proposition that we gave. We're gonna see where is the rightmost collision. So in the end collision algorithm, we were assuming that no collision is happening before the first particle, and there we were finding the rightmost collision. This was the box that the previous proposition was offering to us. Here we're gonna start by searching. So we start in the middle of this left queue, and we'll see where is the rightmost collision of this one. If it is itself, it means that it's not in the big cluster. So for this one, the rightmost collision of this ith one is exactly itself. If the rightmost collision of this particle, for example, is some number greater than d divided by 2, it means that it is in this big cluster in the middle. That's how we're going to detect it. Yep, this is our algorithm, and it has the time complexity of log 3p. Yeah, I'm going to go over the results because, and then we can get back and talk about the time complexities more. First, the first experiment is on CFAR 10. We added the regularization. Along with L, we did multiple experiments, but so the CFAR 10 with, so the baseline is a CNN, and then we took an MLP that is corresponding to this CNN. We trained it with our regularization. And then, as you notice, these are some random weights that we draw out of the weights of the first layer. If you just train an MLP, the final weights will look like the first row. So it's just some random noise, kind of. But if you train it, the MLP with our regularization, you're going to see that some convolution-like patterns are emerging. This is a random draw of the weights. But if you just cherry pick some of them, this is what we did here. So we saw some of these, we saw these look similar. And then you can actually see that they kind of look like the convolution, which is taken over the pixels of the image. So this was cool to see that this convolutional like patterns emerge. In addition, accuracy-wise, we saw that compared to MLP, we could get a better accuracy. The best accuracy was for R plus one, and RR is here. If you notice here, this is what I was what was my motivation for adding L1. So without L1, we do not have a sparsity. The weights are shared very densely. So 99% of weights are shared, but they are not zero. By adding L1, all of these shared weights are gonna take the zero value to themselves, and the model is gonna get more sparse. And the beta lasso is one of the baselines that is trying to create the evolution neural network from scratch. So from this result, you might say that, I mean, why trying to fake CNN when the accuracy is higher? I mean, you just got the convolution-like filters, not convolution. I mean, why not using convolution?
The solution models here, like you have a lot of sparsity, but you don't have weight sharing.
The weight sharing is happening, but all of the weights shared are happening at zero. So the way that we measure the weight sharing is not gonna include them here. It's non-zero weight, yeah. So yeah, let's answer the question of what is the use of this regularization when CNN is working better. It lies in our next experiment, which is MNIST on torus. We kind of rolled the MNIST images pixel by pixel randomly, like roll them from up and right and left, up and down and right and left. And then we created this MNIST on torus dataset. We are training with MLP and CNN here too. And we saw that first CNN, this prediction of asymmetry is kind of a measure to see how the networks can detect, for example, this 7. Let me say how we compute the prediction of asymmetry. We're gonna apply all of the possible rollings. So if this image has 14 by 14 pixels, there are 196 possible movements of pixels that can happen from all of the dimensions. So we create 196 images and see that the model should predict all of them the same. If it's not predicting any 2 of them the same, we're gonna reduce the score of the network by 1. This is how we measure the prediction asymmetry. Asymmetry.
So it has to predict the same, but not necessarily 7.
Yeah, for example, if out of these, all of 196 images that we give a network, it predicts one of them to be 6, we reduce the score.
If it predicts all of them to be 6 when the number is 7?
No, even if one 6, even if all of them are 7 and there's 1 6 in the prediction.
The digit is a 7. But your network is predicting 100% of them, all 6. You get 100% prediction estimate.
We're gonna get 100% predictions. Yes,
Well, that's
imperfect.
That's just one.
And then we're gonna average over all of them.
Yeah, just one instance doesn't give you like a percentage.
Yeah, so basically, so you could have a classifier which always predicts the same thing. You would get 0% prediction accuracy, just bad accuracy.
Yeah. So in prediction asymmetry, it doesn't matter what you predict.
Yeah, it's just that you always predict the same. 2 translations.
Yeah,
Nice.
that's right.
Why did you be so strict with all correct or nothing?
Because the MNIST on torus dataset is already invariant to the translations, so it makes the task easy for all of the models. So we already provided the models with some information from the symmetry of data, so we expect them to be really good.
can you train on all the 196?
No. No. We just pick one permutation of 196 and we train them. And then actually, we do not train on the whole of the MNIST. This result is only for 60% of MNIST. So I take 60% of MNIST, roll it, do a random roll, and create this data set. Yeah, and then we see that CNN gets a very good accuracy and very good prediction asymmetry. It's the perfect one among the, like we have a very, we have a significant decrease in prediction asymmetry, and we have an increase in the accuracy compared to MLPs. But the point of the experiments is where we change data, the same data set, we permute the pixels with a random permutation matrix. In this way, we're gonna ruin the symmetry of the images that it is always there. This is the reason why CNN is such a good architecture, because images have locality and they have symmetry. We are ruining them one by one and seeing them see that if we kind of mess the translational symmetry, the accuracy of CNNs drop very significantly. In this case, MLP plus L1 and MLP plus R, the accuracy of them doesn't change at all. We can prove that if the pixels are permuted, and MLP is actually, the proof is easy. In MLP, you can permute the weights of the network, and it's going to give you the same output. So provably, MLP-based models are now going to change the accuracy, but CNN's accuracy drops significantly. That's the message kind of this paper, that we know CNNs are good given the inductive bias that lies in the images. It is a very good architecture. It gives you perfect accuracy because of these weight sharings. But we're gonna separate the weight sharing part from the CNN. We're gonna learn it in the MLP such that when you're training an image data set, it's gonna learn that biases, it's gonna learn the convolution-like filters that CNN has. And in addition to that, if you remove the translational symmetry, it's gonna still have the same benefit because it has learned the correct weight sharing patterns. It can adapt itself to different inductive biases of the data. Yes, that was it.
So here you said you would remove these things by permuting the pixels?
Yes.
So if you permute the pixel, you're basically removing the locality and translational symmetry. How do you just do, what's the difference between line 2 and 3?
Locality and symmetry. So if so I'm creating the data set, do I have so if I just first permute, so in the MNIST, I'm doing two actions, first permute, then roll. If I do the permute first and then roll, I'm just ruining the locality because the rolling is gonna produce the translational symmetry. But if I roll first and then permute, it's gonna ruin the translational symmetry.
Ruins
Both locality and answer. And this was a cute observation too. I mean, it was a side observation, but it means that CNNs do not care about locality as much as the symmetry. Because, I mean, if you take one course on CNNs, you see that they use this locality of images, they use the symmetry of images. In this experiment, we offered that they care about locality less. That was my presentation, but I get more questions.
Price.
reference, more reference, and an appendix list.
We have time for your question once ready to take the last question. We have plenty of questions also during the talks.
What about the running time?
Okay, this was something that I should have mentioned. Now that we have time, let me go.
You can go to the appendix already.
Here you could have done any
Appendix
of
is not
these-
good.
you could have done any of these experiments with any of the algorithms.
Exactly.
In theory.
Yeah, in theory, but first we offered the parallel version of these sequential algorithm. As we saw, like each of them has this power in some setting. Imminent collision was good when the number of collisions were small. The end collision was good when the number of collision was too much. And our algorithm was best and like it has best worst case complexity. However, I should have mentioned it actually, I forget. But first, I should say that it was a challenge for us to reduce the time complexity of model. We iterated over our algorithm multiple times. I mean, we started on runtime of 120-hour MNIST, and then we got to the 4-hour, which is typical. Like a SGD simply on MNIST in my setup will run on 1 hour, and at the end, the imminent collision was running on 4 hour, and all algorithm was running on 8 hours, I guess. So we provided the runtime per epoch for all of these methods. But at the end, imminent collision was working better, surprisingly. We have an example in our paper. I mean, it's obvious that there is a worst case example in which our algorithm is working better because we have a better worst case complexity, and we have it in our appendix. But yeah, it's imminent collision apparently is working better for this type of neural network structure. That's what we concluded at the end. This is something that needs to be worked on more even in the future, because still we are getting this nice results, but our runtime, even our best runtime algorithm, is multiple times the normal SGD. So this weight sharing is, I mean, it is heavy. And as you saw, people were hoping to solve it for 110 dimension only. But yeah, some more work needs to be.
Seems like the algorithm is very expensive because you're trying to solve the clock step exactly at every step. But in the context of stochastic optimization, we're not even using the exact gradient at every step. Do you really need to solve the clocks exactly at every step?
I mean, we were thinking about not solving it exactly, but yeah, given that we had all of these tools to compute it exactly, we rather to compute it exactly and then do the non-exact solution in the future works. But we didn't really give it a thought on what would happen if we don't solve the procs exactly.
Because, for example, here in the reference case, then you're doing, one and then a sequence of zeros. Then doing the entire process might take a long time, but you could do a few steps of it. And then over time, if because of the inclusion, you could get to the weights are of course going to move in different ways. But could it be the case that through doing this process sequentially over time, you could get to a close enough solution to doing it exactly at every step? Yeah, that's a good research question, definitely. Yeah, we didn't do experiments on this, but I mean, Meron, if you have more intuition on this, you can share.
A quick comment on that. So usually solving the proxy exactly is quite important for both the convergence and sparsity, because what does it mean if you don't solve the proxy exactly? That means you have either sparse things, so you say, okay, I don't want to go, or you consider the solution, but it doesn't guarantee the solution is sparse. So there are plenty of questions of what is solving a prox exactly means. One other solution instead would be the prox kit, which is used in federated learning, where you do many steps of stochastic regression and then you apply prox randomly. during the process, and that may help a lot in terms of
What is the concept of solving a prox exactly in any way complicated? The prox is an optimization problem, and we solve optimization problems exactly all the time.
Yeah, but so there are theory about the inexact prox method, but here the prox is mainly used for the sparsity aspect of it. And most of the time, when the theory that has been made for inexact prox method is when you're considered to be close enough to the solution. Thing is, being close enough to the solution doesn't guarantee you that your solution is sparse.
Exactly.
And
And I want to mention this line too, yeah. This line is our experiment with R, but with stop gradients method. And as you see, like the weight sharing didn't really happen. It performs like the NLP. In this constraint that we have, this is one of the sub-gradient methods. So maybe solving it inexactly, it's not gonna help because of this mess that is going on in the non-differentiability points.
So perhaps to clarify here, there's two directions of efficiency. One is to do an exact prox. The other one is just to do the prox less often. So the one that I mentioned, which was done for learning, which was done much before that, it's called, they're basically called two-loops algorithm. So I guess, like where, for example, for projected, the more standard one would be just instead of doing the projected variant method where you project at every step, you would just project at every case steps or whatever with some schedule. And so if the projection is expensive, then you can get. And so prox skip is the same idea. Is you would only do the prox at every few iterations. You do a bunch of local steps. So that definitely is okay. In exact, like as mentioned, it's a different direction. It has a bit of issues with getting the sparsity itself, but also could be explored.
That's right.
How do you tune the, I mean, this is the forbidden question in regularization. I mean, the most,
She didn't know what's your question.
most importantly, so you have, let's say in the case, so if you have R, the big R, how do you tune, how sensitive is the method to the coefficient that is used for that optimization? And two, how do you balance it with the L1?
For the L1, we're just tuning between three existing popular choices. And the same for R actually. I mean, I cannot say that now. This is what we prescribe actually. In the process of making the paper, we used many learning rates, but what we prescribe is to kind of tune the R regularization coefficient in the range that you are tuning the L1 regularization. So in the range of 10 to the minus 2, 10 to the minus 3, 4, and 5. That's what we tried. And for the L1, we tried 10 to the minus 2, 3, 4, 2. Yeah. So the ranges are the same. If you want to tune, I would say, yeah, tune it like L1.
And so, and how sensitive is the algorithm to this choice? Say if I choose 10 to the minus 1, then nothing, there's not much clumping together. If I choose 10 to the minus 4, then or the other way around, then everything just sticks together. What's the sensitivity here?
So I think that it changes from one problem to the other. I think there should, if you select, for example, more than 1, it's going to be too sticky, and less than 10 to the minus 6, it's not going to do anything.
Australian version.
Your words, no.
So if you can do the process, you can project that. So if I say R of W smaller than some value, I could project on this set.
Well, that's a bit tricky. You kind of have to do some kind of search on how strongly to perform how large the box then. You kind of binary search, right? On the step size of the box, keep multiplying by 2. Whenever you've gone too far and the R becomes too small, you go back 1 step and now do smaller step. Let's take it.
Good.